Section 5.8, Application of Polynomial Equations. In this first problem, we're given that f of x is equal to 3x squared minus 4x. Find all values of a for which f of a is equal to 4. So to start out, we will replace f of x with f of a. Everywhere there's an x, we will replace it with an a. Furthermore, they're telling us that f of a is equal to 4, so by substitution, we'll replace the function notation with the value of 4. What we have is a quadratic equation that if we're to solve this, we'll put it in standard form, which means one side of the equation is equal to 0 and all the terms are on the other side. We'll accomplish that by subtracting a 4 from each side. And right now our technique is, given a quadratic equation, is to factor it and then use the zero product property. There is no common factor other than 1. Because the leading coefficient is an integer other than 1, we can use the guess and check as one of our techniques. We could also factor this by grouping. But because these aren't, this is a prime number and this one is an extremely large complex number, we can probably get there with a guess and check faster than using the factoring by grouping technique. For negative 4, we have a choice of negative 1 and 4 or negative 2 and 2. And after doing some checking, I believe that this is the correct factorization of this quadratic equation. Just to check, first terms multiplied together is the 3a squared. Outside we would have a negative 6a, inside would be a positive 2a, which is a negative 4a, and last terms multiplied is the negative 4. The zero product property says that two things multiplying together resulting in a 0 means one or the other of those factors is 0. So either this term is equal to 0, and if we solve for a, we'll subtract a 2 from each side. And then to get a completely by itself, divide through by 3, leaving us with a solution of negative 2/3. Or our other solution comes from the fact that this factor could equal 0. And solving for the value of a that arrives at that is when a has a value of 2. So our solution for this problem is negative 2/3 and 2. In this next problem, they're giving us two functions that have polynomials equal to them. F of x is equal to the following, and g of x, it says find all x values for which these two functions are equal to one another. So we will replace f of x with its equivalent value equal to g of x, and we'll set what it is equal to. This is a polynomial, and to solve a polynomial equation, we're going to put it in standard form. So bringing the 9x squared to the left so that we have a 0 on the right, and putting these in numerical order since they aren't similar term. By numerical order, I'm implying decreasing powers of the variable. So 3x to the third minus 9x squared minus 30x. We'll park that squared term in between the third and the first power. Looking for a greatest common factor always when we're factoring is a good place to start. There's a common 3 and an x here. We'll factor out a 3x, which is dividing. 3x to the third divided by 3x leaves x to the second. 9x squared divided by 3x will leave us with a 3x. Negative divided by positive is a negative. And negative 30x divided by 3x leaves us with a negative 10. So we have our greatest common factor. It's always a good idea, multiply to make sure there wasn't an error, that we do have an equivalent expression. And then if we look at this trinomial, we can factor further. Because the coefficient is 1 here, we're looking for factors of negative 10, one positive, one negative, that add up to be negative 3. So we have a choice of 1 and 10 or 2 and 5, and doing some testing, We find that a negative 5 and 2 do the trick. Again, a quick multiplication. First terms, there's the x squared. Outside would be a 2x. Multiplying your inside terms would be a negative 3x, which do add up to be the negative 5, which do add up to be the negative 3x. And then last terms multiplied together is the negative 10. We now have a product of three things multiplied together to equal 0. Either 3x is equal to 0, or x minus 5 generates this equation to equal 0, or the possibility that the last factor, x plus 2, equals 0. Solving for the x then, dividing both sides by 3, 0 divided by anything is 0, so 0 being one of our solutions. Adding a 5 gives us 5 as one of our solutions, and subtracting 2 on this last option gives us negative 2 as a possible solution for this equation. That means our solution contains the set 0, 5, or negative 2 would be the values for which these two functions are in fact equal to one another. In this next example, they're asking us to find the domain of the function f of x defined as given. When we're solving problems like this, the domain of the function is the set of all values for which f of x is a real number. Since division by 0 is undefined, we cannot let f of x be calculated at an x value for which the denominator is 0. So to make sure these values are excluded, we're going to solve this equation in the denominator for when it equals 0, something that we want to avoid or restrict in the domain. So solving this, we will take x squared minus 7x minus 18 and set it equal to 0, something that we want to avoid. We're looking for factors of negative 18 that add up to be negative 7, one positive and one negative. 1 and 18, one being positive, one negative, doesn't work, but a 2 and 9 do work. And it turns out if we have a positive 2 and a negative 9, when you multiply those together, FOIL method, outside would give us a negative 9x, inside is a 2x, which is the negative 7x, last term is the negative 18. The product of these two things then is equal to 0, which means x plus 2 equals 0, or this factor must equal 0 for the product to be a 0. Subtracting a 2 from each side, we end up with x is equal to a negative 2 would cause the denominator to equal 0, something we're trying to avoid. Or if x is equal to a 9, we would end up with a 0 in the denominator. Both of these are things that we want to avoid. So if we use our set notation, we would say x for the domain, I guess I should write that, the domain is such that x is a member of all real numbers except x cannot equal a negative 2 or a 9. If we're using interval notation, we would have the following. Our domain could be listed as a negative infinity up to negative 2. We're not including negative 2, so we would put our parentheses, and infinity always has the parenthesis, union with negative 2 to 9, all the numbers between there, but not including them. So to show the non-inclusion, we use parentheses, union with 9, starting with 9 but not including it, anything greater than 9 up to positive infinity. This would be our expression for the restriction on our domain for this problem.